Hey there students, it's Mr. C. I'm in our classroom and this video will be a short recap of limits that we've seen so far, limits from 1.5. In 1.5 we took functions like this function, f of x equals 1 over x, and we would take a limit at a particular value of that function. And we did it three ways. Way one, graphically. You know what the graph looks like? You can figure out the limit. Two, numerically. This is table of values. It's brute force calculation. You don't quite know where you're at, so you create a giant table of values and you see which way it's going. Option three was algebra, and the clue we said here is you plug it in. Whatever x value you're approaching, plug into the f function, find out what f of x is. And they're a great way to corroborate. In section 1.6, we get exclusively into the algebra. So here's a recap of 1.5 to kind of get you there. I'll keep it brief. Let's take a look at this function right here. F of x equals 1 over x. What's the name of the function? F. What's the independent variable? X. What's the dependent variable? F of x. What type of function is it? It's a rational function. It's a quotient of polynomials. The numerator is a polynomial of degree 0, a constant linear function. The denominator is a polynomial of degree 1, a linear function. And you know what it looks like. So we can handle it graphically. Now, if I asked you what's the limit as x approaches 0 of f of x, what am I saying? I am saying as x approaches 0 from both directions, what is f of x approaching? That's what's being said. So you have to think about approaching 0 from both directions. So break it up in your head. As x approaches 0 from the left-hand side, what does f of x approach? And as x approaches 0 from the right-hand side, what does f of x approach? Let's take a graphical approach. Okay, here's your graph of 1 over x. You know it, you memorized it. You know there's an asymptote here, a vertical asymptote at x equals 0, a horizontal asymptote at y equals 0. You know what this graph looks like. So, if I ask you what is the limit as x approaches 0 from the left, here's what you do. You just approach x equals 0 from the left, and you follow x comma y, which is any point and every point on the function. And as you can see where the y values are going, where the f of x values are going, they're going down to negative infinity. So we would write up here, negative infinity. As x approaches 0 from the right, what's happening to my x comma y values? Well, those are the values on the graph. You can clearly see, therefore, where are my y values going? My f of x values, they're going up to positive infinity. Now, for a limit to exist, a two-sided limit to exist, the right-hand limit and the left-hand limit have to be the same. They are not. Therefore, we say the limit DNE does not exist. We don't write that the limit's undefined. We say it doesn't exist. That's the language you use most frequently. All right, that's the graphical approach. Let's try the table of values. If this function wasn't familiar to us, or we forgot what the graph looked like, we could take a brute force table of values approach, a numerical approach. And here's what we do. We say we got to get some x approaching 0 from the left-hand side. So what's just a little bit less than 0? Something like negative 0.1. And a little bit closer to 0, negative 0.01, and then negative 0.001, and so on and so forth. Or we could approach x from the right-hand side. Start at 0.1, then 0.01, then 0.001, and so on and so forth. You set up a table of values and just plug in the values. If I plug in negative 0.1 into this function, I get 1 over negative 0.1, which is negative 10. If I plug in negative 0.01, I get negative 100, negative 1,000. Now clearly the trend here is to negative infinity. As x approaches 0 from the left, f of x approaches negative infinity. Likewise, if I look at x approaching 0 from the right-hand side, well, f of x, 10, 100, 1,000, clearly approaching positive infinity. And isn't that what we said with the graphical approach? Left-hand limit, negative infinity. Right-hand limit, positive infinity. Therefore, once again, the limit doesn't exist. Got it? Good. Last approach is the algebraic approach. The algebraic approach really isn't going to work for us here. This is too simplistic of a problem to really be useful. but we just want to remember what our approach is. The approach is very simple. If I take the limit as x approaches 0 of f of x, just take the limit as x approaches 0 of f of x, that's f of x, right? And I just plug in the value of x that's being approached into f of x. Plug in 0, get 1 over 0, that's clearly undefined. Whenever you have a real number that's not 0 divided by 0, that's undefined. We don't say that the limit's undefined, not really. What I'm saying is if you had used the algebraic approach where you plug 0 in to f of x, this rational statement would be undefined. Same thing would happen if I approach from the left or I approach to the right. If I plug in 0, get undefined, undefined, undefined. This doesn't really answer the question for me. You might say, well, of course it does. Look, the limit doesn't exist. It's kind of coincidental. Algebra doesn't give me much information in this case, but it will. All right, let's look at a case where the algebra does give us some information. All right, here's what we're going to do this time. We're going to choose a more advanced rational function. All right, clearly it's a rational function, a quotient of polynomials. X squared minus 1, polynomial degree 2. Denominator, polynomial of degree 1, linear. All right, so if I asked you for the limit as x approaches 0 of f of x, what am I asking you for? I'm asking you for the limit as x approaches 0 of whatever f of x is, which is x squared minus 1 over x minus 1. Now watch what happens when I attempt to use the algebraic approach. Remember, we're going to talk about the algebraic approach. I just plug in the value that x is approaching into f of x and see what I get out. Well, if I plug in 0 here, I get -1 and I get -1. So the answer is 1. That's it. I'm done. I didn't even have to think about left hand and right hand in this particular case, did I? But that's not really the interesting limit. The limit as x approaches 0 of this. That's not interesting. What's interesting is the limit as x approaches 1 of this guy. This is the interesting case. We don't have to worry about these guys right now. All right. What happens if we take the limit as x approaches 1 of f of x? Well, again, plug in the value that's being approached into f of x, and you get 1 minus 1 over 1 minus 1, which equals 0 over 0. This is called indeterminate. Indeterminate is 0 over 0 or infinity over infinity, or negative infinity over negative infinity. 0 over 0 will often show up. These are indeterminate forms. Let me tell you what indeterminate means. It means I don't know. Or precisely, I don't know yet, because maybe I can do some algebraic manipulation that will show me the answer. It doesn't mean this thing does not exist at all. It just means I don't know yet. When this happens and I'm taking an algebraic approach, I go back. So here's why I go back. And I say, how can I algebraically manipulate this guy right here so that this works better for me? Well, here's what I'll do. The numerator is clearly a difference of perfect squares. And you can see it already. X minus 1 divided by x minus 1 is 1. 1 times x plus 1 is x plus 1. So I could rewrite this guy as the limit as x approaches 1 of x plus 1. If you're wondering, are these the same function? Not quite. This is a linear function. What linear function is this? This is slope 1, y-intercept 1, shifted up 1. This guy, same deal, except you have a hole here at x equals 1. Okay, so for limit perspective, these two are equivalent. This function is not quite the same as this. Domain here is all real numbers. Domain here is all real numbers except for 1. Doesn't really matter for a limit, because a limit is you're getting infinitely close to something but never getting there. So you can miss a point and still be okay. Unlike a test, but all right, here we go. So as x approaches 1, what does x plus 1 approach? Well, plug and chug. Whatever x is approaching, stick it into f of x. You get 1 plus 1, which equals 2. Because really, this is like that. Or realistically, it's like that. See? If you were to take the two-sided limit as x approaches 1 from the right, y seems to be descending to 2 from the left. Y seems to be rising to 2. Doesn't matter there's a hole there because we're talking about limits. Getting infinitely close to something but not actually getting there. This is algebra. You're going to be doing a lot of algebra, starting with the limit laws, in section 1.6. So I hope you're now reminded about what you're going to do with 1.5. Thank you.